Thank you very much, Sagar. Good morning, everybody. Indeed, I want to tackle workflows from a bit different perspective that was discussed before, but my first claim would be that without metadata, the complexity is not handleable at all. That's the first claim to make. Because I am a senior scientist who has worked for quite many years in different projects, European and national. They are all related majorly to data-driven systems, or expert and data-driven systems, monitoring and control on permanent basis of different infrastructures, but also biodiversity digital twins of electrical grids, cooperative driving, etc., etc., etc. So let's start with what is actually workflow. When we talk about the workflows, so the key elements are the tasks or steps. Then they should be organized in some sequence or a graph of execution. Then, of course, if we talk about the workflows where maybe multi-parties are involved, that means that we will have different business roles for the people, because you would have end infrastructure providers and modelers and data owners, and you need to organize them all in right, let's say, fashion. Then also for the workflows, what are important are rules and conditions, also constraints on what is available, what is possible to run, how to connect maybe the models, how to connect sometimes different infrastructures, or how to make the connections to IoT devices. It's all kind of should be handled through specific rules, where also metadata plays a role. And of course, the workflows nowadays don't exist without inputs and outputs. So literally, when you talk about tracing workflows, you don't only need to trace the models and their results, you need to start from the data inputs, from the right versions of the data sets that you use, then through the whole models and processing steps till the output. Kind of people separate, the community experts separate the workflows to different categories. So let's start with the sequential. It's the easiest one, it's a pipeline. So it's one step after another, and you have kind of a line. So you know that you have an output of the first step, which becomes the input to the next step. Right? However, of course, it's not always possible. In many cases, workflows are more complex, and that means parallel workflows where you have kind of the branches that you need to calculate separately, but then merge the results sometimes. And sometimes it also goes to the next phase of separation of the branches and then back to the results. That's already a bit complicated, but it's not all, because then we move to the conditional workflows, and that is where we have some conditions. So for example, we have different models, and you would apply a specific model, you choose the model according to the specific condition after some pre-processing or after the first step. And then it complicates workflow, because then you need to organize it, automated, let's say, handling of different models and the choices. It's not all, because the next step is when we talk about iterative workflows, when, for example, probabilistic workflows, when we have iterations, and if something doesn't converge, you need to repeat it. And that is also where the reproducibility is the most difficult with such type of workflows, because they're iterative and you need to kind of save even every step of them. Otherwise, it's not possible to trace them back. A special case of the workflows are co-simulations. When you have different models, for example, MATLAB, Simulink models, and they need to speak to each other. Good luck to organize the communication between them. So it also increases the complexity in its own turn. So actually, when we talk about complexity, kind of the easiest is surprisingly parallel, because you simply can run them. You don't care about the communication between the branches. You just save the results, and then you can reuse the results. Second place from that easiness is sequential workflow. So that is when we have more complex graphs, not one pipeline, but when it's sequential, but it could become quite a complex graph of execution. And that is, it requires not only handling of distributed data storage, not only efficient memory and cache, but also you need to control that it's the right order of the task, that it's the right communication is being handled between the different steps, and that you save all intermediate results of all the steps, because otherwise you cannot reproduce it at all. The problem is with conditional and iterative workflows. That's where complexity explodes enormously. And I do believe in the examples, so I want to provide you, to lead you through some examples that we have had in some projects for such workflows to demonstrate you the complexity and how it's possible to handle it. So one of the projects in which we participated was on national level to predict chance of failure of all water and gas pipelines of the Netherlands for the next 30 years. What does it mean? You need to check the materials of the pipelines. You need to check where do they lay, because urban area would differ from the landscape, agricultural landscape, for example. And then you need to check the water, then you need to check underneath, underground materials, etc., etc. That means many probabilistic parameters. We are not sure what actually is underground, not at every place. So it's quite a complex workflow, and it's also the workflow from different organizations. And we have had 10 different models from different organizations that we needed to combine, and around 30, I think, different data inputs. And in the end, it has grown to 400 stochastic parameters combination. That is normal type of workflow when you talk about probabilistic workflows. So what we needed to do, we needed to take the geographical map of the Netherlands, make a grid, and actually for accuracy of the results, we needed to make the cells of 70 by 70 kilometers. And for every cell, also to make smaller, let's say, subcells, where we would try to calculate the result. The problem is, for example, with the underground information. You see the red dot, you know only exactly one dot, maybe what happens underneath, what is sand, what is clay there, or something, only that dot. So you need to interpolate properly into all other subcells. Because in the Netherlands, yes, it is checked what is underneath, but it's every 60 kilometers. It's not enough. So that's why we have the probabilistic profiles of the underground in this case. And in the end, you start with the probabilistic parameters. You take historical data. Sorry for the Dutch here, but I really needed to use how it is. Also, the historical, let's say, trends on in urban areas. So what was developed, which buildings, when, where, because they would also pressure the pipelines, actually. Then you would take the water. The Netherlands is beneath, let's say, the water level. That's why the water in the underground is also important to take. And then you run probabilistic models that provide you the state now, that provide you the trends, and then you can kind of combine the parameters properly to receive that failure chance for the pipelines in the end. That's actually around 10 models, and that you see, we tried to put, okay, where do we have the data sources, where do we have the models, and how to combine them. In the end, every rectangle here is a model. And again, as I said, many data analysis. However, it's not yet probabilistic computation. It was just to calculate intermediate result on the sensitivity of materials and the sensitivity to the different factors. It's not even yet completely probabilistic. However, it's already conditional workflow. And here it's very complex workflow, so don't look into details. I only want to pinpoint you to the N and M variations, because in the end, when you start to elaborate such workflow, you come to the many stochastic combinations. And here we have had 2M by N, that meant in our case 400 calculations. So you need to elaborate such workflows properly, first logically, to be able to understand how much do you need to run and which combinations you need to check. In the end, we used also added iterative workflow because it was needed for probabilistic calculations, because we needed the chance. So we did it in Monte Carlo fashion. We explored 400 combinations, and actually with our acceleration, we reduced runtime from half a year that was before trying with all manual steps to 4 days. So we did have that chance. Very important from that lessons learned. It's about composition of the workflows, because in the end you have all the probabilistic models. You need to have somehow a controller. So here I want to pinpoint you to the monitoring step, which is actually the controller, which above checks all the sub workflows and guarantees that they should be in done in right order, and that you save all the intermediate results before you can continue to the next phase of iterative processing. So you need such a controller above your even workflows that you already compose. When we talk about multi-party computations, and that is what we also have had, it's also much more difficult, because sometimes other parties provide you the models, you can run them yourself, but sometimes not. Sometimes it does run as a service at their premises, so you need to make the calls. Situation is even worse when you need to involve IoT devices, which happens a lot on the domain of digital twins, in which I'm very busy with. So that means that you need some other techniques, some other types of workflow, which are more like federated learning workflow, where you allow actually local computations happen on IoT device side or on other infrastructure side, and then you run in parallel your global model, and then you need to arrange the connection between them. There are first attempts to make it happen with some open source tools. I would be happy to talk about it. But again, it's a different type of distributed, let's say, workflow, which doesn't only depend on data lake infrastructure. And also it's not, because also for federated learning, there are different types. It's the easiest is horizontal federated learning, where think about mobile, think about yourself, and then, for example, calculating the movement. It's the same model which is pushed to all mobiles. So you have the same parameters. That is horizontal. Vertical model, it's easier to handle. Much more difficult is vertical federated learning, where you have your mobile, you have your data, hospital has some other data about you. And first, the analysis should go to you, and then back, and then to the hospital. So to combine the parameters together, it's also more difficult to handle. And the last one is transfer learning. It's more probabilistic, because it's about let's learn what is happening with, for example, you yourself, and try to interpolate it to other people. Transfer learning. And there you need to check the similarity status. So we have done it for digital twins of electrical grid, and the electrical grid operator doesn't have the right to access the household energy consumption information. So in the end, we have had local models in households, then semi-global model, which was actually merging and anonymizing all the results, and then only then it has gone to global model to the grid, and that should have run on permanent basis. So for multi-party, extra processes to handle are actually not only workflows, but APIs. I'm now looking at Sandro, which is very important to have standardized APIs, RESTful APIs, security, and communication reliability. The last case is co-simulation. And it's a special case, however, when you have long-running simulations, which, we, for example, we have had in biodiversity digital twin project. So they run in different frameworks. They have their own cycle of life. However, sometimes they need to change information. For example, for the species which live in the forest, it's good to know what is the season and how the forests are evolved in time. So you need to have special flags. You need to have a buffer between the different simulations and provide extra functionality to let them listen to the requests, to send the data, and to use the data when it's needed. So all that just a demonstration how complex workflows are. So my conclusion is workflows are complex. Actually, they are handleable. It's an effort for end modelers and infrastructure team, and it's common efforts that should be done. Multi-party workflows lead to handling with external data, and all that requires flexible architecture for future-proof computing. So I leave this last slide just for as a teaser if you want to discuss, because we try to construct more like what is a common effort, what are workflow types, their characteristics, and key infrastructure needs. Thank you for the attention.